Hello everyone. For this tutorial video, I'd like to explain word problem applications of quadratic equations using real-life scenarios. If we are asked, two cars start at the same point. One car drives north at 25 miles per hour, and the second car drives east at 20 miles per hour 2 hours later. And how long does it take for the two cars to be exactly 300 miles apart? We would figure this out by doing distance of car A equals 25 times t, because of how distance equals speed times time, by a rearrangement of the speed/velocity equation, and distance of car B would be more complicated because of how it starts 2 hours later, but it would be 20 times t minus 2, where the minus 2 is important because it loses 2 hours from the total time to waiting. We also remember that we were given specific directions for each car, so we plot this out and see it forms a right triangle, where the distance between the two cars at the point is the hypotenuse, which measures 300 because we are given the distance is 300, and the legs are given simply by the distance equations for each car. We now apply the Pythagorean theorem. See that the left term and the constant on the right hand side of the equation both square out neatly, but the right term on the first hand side does not. But if we stop to think carefully about how this distributes out, we get an answer of 400t squared minus 800t minus 800t, which simplifies to minus 1600t plus 1600. We now get it in terms of a standard quadratic equation by subtracting the 90,000, and we can now plug in all of our values in the quadratic formula and see when we compute exact answers that do not involve square roots. The second answer to the quadratic formula gives us a negative value, which is not physically possible, i.e. time only flows forward. So we conclude that in the context of this problem, t has only one value, which is approximately 10.01. So the time when these cars are 300 miles apart is approximately 10.01. If we are given a problem involving office work such as this, an office has two envelope stuffing machines and, working together, they can stuff a batch in 2 hours, and working separately, it will take the second machine 1 hour longer than the first machine, and has to figure out how long would it take for them to do it by themselves. We would do this by first deriving the formula: the portion of the job done by machine A plus the portion of the job done by machine B equals one full job, and the portion of the job done by each machine would be given by the work rate of the machine times the time spent working. So we plug in this formula. We know that the first machine takes t hours, and the second machine takes 1 hour longer, so it takes t plus 1 hours. So since we want to know the work rate for one job, we can get an exact formula for the work rate of each machine by dividing 1 by the time each machine takes. So we plug these in into the equation work rate times time plus work rate times time equals 1. We are given explicitly that the time the machines work collectively is 2 hours, so we plug this in for the time. So now we get the left hand side in its most simplest form, and then multiply everything by the least common denominator to get rid of the fractions, and see that unfortunately we get a quadratic equation on the right hand side. We simplify the left hand side, and then get the left hand side equal to 0 by adding and subtracting terms as appropriate. We now do the quadratic equation and see that unfortunately the second answer to the quadratic equation gives us a negative value for t, and we established in the previous example that time can only physically go forward, so we discard the second answer and see that the time can be exactly equal to only one value, which is approximately 3.5616. So that is our answer for how long it will take machine A to do one job by itself. And even though the question may not have asked it, we can predict that machine B will take this value plus 1, so it will be 4 point, etc., where I use etc. because it is the same exact value after the decimal point, so I do not feel a need to reiterate it. Now that I've explained applications of quadratic equations in standard form, we can discuss equations reducible to quadratic form next, which I mentioned briefly existed when I discussed factoring quadratic expressions, but I will not show you a specific example until the next video. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.